Welcome back, everyone. We're going to try out another example regarding linear transformations. So here's another example for you. This one we're posing the question, is T a linear transformation? This time we have T takes us from the domain R3 into the codomain R4 given by T of x1, x2, x3 is equal to. The first three components will all be the same, but the last component will be the sum of the first three components. So like we did on our last example, just for funsies, I'd like to figure out what the image of a vector looks like. So I'm going to grab a vector from within R3. This one will be 1, 2, 3 for the vector in R3, and we're going to transform that through our transformation into R4. So R4, the vector should have four components. The first component should be the same. The second component should be the same. The third component should be the same. And the fourth component should be the sum of those three components, 1 plus 2 plus 3, which I totally used my calculator for, and I got 6. I'm just kidding, I didn't really use my calculator for that. It's probably better that I didn't. So anyway, what we're really trying to test is T a linear transformation? So once again, we're going to need two generic looking vectors in our domain. So generic looking vectors in our domain will look like this. They will be vectors that have three components, like so. So we'll take the vector x, which will have components x1, x2, x3, and the vector y will have components y1, y2, y3. So the thing that we are testing, is it true that t of x plus y is equal to, question mark, t of x plus t of y? So first thing I'm going to do is add these two vectors together over on the left-hand side. Adding two vectors together in R3 means we add their corresponding components together. So first component will be x1 plus y1. Second component, x2 plus y2. Third component will be x3 plus y3. The question is that the same as the transformation of the vectors x1, x2, x3? Plus the transformation of the vector y1, y2, y3. So now that we've expressed both of these sides as the transformation of a vector, we get to go back to the definition of the transformation. The transformation takes the vector from R3 and says first components will be equal, second components will be equal, third components will be equal, and the fourth component will be the sum of the previous three. So first component will be the same as before. Second component will be the same as before. Third component will be the same as before. Excuse me, that should be a comma there. x3 plus y3. And then the fourth component should be the sum of the previous three components. So that'll be x1 plus y1 plus x2 plus y2 plus x3 plus y3. Now, let's transform our other vectors as well. We know what t of x1, x2, x3 should look like. That should be x1, x2, x3, and then the sum of those three components. The transformation of the vector y should look approximately the same. y1, y2, y3, and then the sum of those components. y1 plus y2 plus y3. So once again, we get to pose the question, are these two things equal to each other? Well, the thing on the left-hand side is about as simplified as it's going to get. We need to simplify the right-hand side. So rather than recopying the left-hand side, I'm just going to go ahead and add these two vectors together on the left-hand side. Now these are vectors in R4, which means that I add them by adding together corresponding components, as is the standard operation. So add together the first components, add together the second components, add together the third components, and then finally, add together the fourth components. So this will become x1 plus x2 plus x3 plus y1 plus y2 plus y3. Then we're going to do a quick analysis of our new right-hand side vector with our old left-hand side vector. So we got first component, those are equal. Second component, those are equal. Third component, those appear to be equal. Fourth component, and let's make this one snazzy. And fourth component. Now, using the commutativity of the addition function of real numbers, we can see that these two things are in fact going to be equal to each other. So, this is a good start, but this is only half the battle. So we can say, thus, T preserves, there we go, vector addition. But as I mentioned, that is only half of the battle. So the other half of the battle comes in the other property of linearity. Let's go ahead and trade this out. Get a new sheet here. So we'll keep our linear transformation up top. The other thing that we need to check is, does T preserve scalar multiplication? So using the same definition of x that I used just a moment ago, I also want to check to see, is it true that the transformation of some scalar times x is the same as that scalar times the transformation of x? This is the thing that I would like to check. First thing I'd like to do is actually write down what c times the vector x would be equal to. So c times the vector x, we would be using the standard operation of scalar multiplication. This would be c times x1, c times x2, and c times x3. Over on the right-hand side, I would have still just c times the transformation of x1, x2, x3. Now, both of these sides are in the form of the transformation of something, so let's go ahead and send that through the transformation. Now, the transformation is supposed to preserve the first component, second component, third component, and then the last one should be the sum of all three of those components. So this would be c times x1, c times x2, c times x3, and then the sum of all three of these. Then we already know what the transformation of our standard vector is here, x1, x2, x3, and then the sum of all three, x1 plus x2 plus x3. The question is still, are these equal to each other? Because we're not 100% sure yet. Over on the left-hand side, we're just going to leave that exactly as is, as nothing really additional needs to take place there. Cx1 plus Cx2 plus Cx3. Now, according to our standard operation of scalar multiplication in R4, we're supposed to distribute this scalar c to all four of the components. This would be c times x1, c times x2, c times x3, and then c times the quantity x1 plus x2 plus x3. Now at this point, we're going to analyze the four components and say, are they equal to each other? First components, hopefully that'll be pretty easy to see that the first components are equal, the second components are equal, and the third components are equal as well. Now, according to what property are the fourth components equal to each other? Oh my gosh, I feel like Dora the Explorer. That's right! It's the distributive property! So if we were to distribute the scalar through to all of the components that are in here, all of the terms that are in here, these would be exactly equal to each other. Thus, we can say that T preserves scalar multiplication. Now, as soon as you have that it preserves both vector addition as well as scalar multiplication, you're allowed to get to your big important conclusion. I like to use the triple dot for therefore on our big important conclusion. Therefore, T is a linear transformation. And that one felt pretty good, so I'm going to give it kapow. I hope that this was insightful for you. I hope you understand a little bit more about verifying linear transformations. And I'm sure I'll see you all again for a new tutorial sometime soon.